This video briefly talks about the normal distribution. We know some continuous random variables, they have very special distributions, and they get their own names. In this video, we're gonna briefly discuss the normal distribution. Sometimes it's also called Gaussian distribution. This is a very important, probably the most important continuous type real value random variable we're gonna introduce in this course. So this is the first video introduce this distribution, and in the future you'll learn more properties associated with this special distribution. When we talk about continuous real value random variables, in this course we always start with the PDF function. The probability density function PDF is designed specifically for continuous real values random variable. And before we take a look at the PDF function of a normal distribution, let's first look at one example, right? Why do we need this normal distribution? Suppose there is a super server receiving many requests from independent computers 1, 2, 3, until n. The number of requests from each computer within a time interval of unit length ni, so the number of requests from the computer I, would follow independent identically distributed Poisson distribution with arrival rate equal to 1. Now suppose one is wondering about the distribution of the number of total requests when n is getting larger and larger. Okay, so he wants to know something, learn something about the number of total requests, and decided to look at this following random variable, which is, well, summation of ni shifted by its average and then rescaled by the square root n. So this is the sample summation shifted by the average divided by a square root n. Given each ni, each ni follows identical distribution with arrival rate equal to 1. So the expectation for the Poisson distribution with arrival rate equal to 1 is simply 1. What is the distribution of this random variable? You can pause the video at this moment and think about it. Well, we know ni, they are independent and follows identical distribution, Poisson distribution with arrival rate equal to 1. Therefore, the summation here, summation of ni, is a sum of IID Poisson distributed random variables. And we know sum of independent Poisson is still Poisson distribution. And for this special case, this summation follows Poisson distribution with arrival rate equal to n. Therefore, based on this, we can calculate directly the CDF function of the term in color red, right? The probability of this term smaller or equal to a given number up to number m is essentially equal to the probability of this summation is smaller or equal to this number. Given the fact that this summation follows Poisson distribution, we know it can be calculated by this way, right? So sum all the integer numbers from 0 until the closest integer, the integer right above, below or equal to this number here. We're gonna sum up all their probabilities together, which is the CDF function here. This looks very complicated, right? But surprisingly, this monster has a limit when we let n grows larger and larger. So actually, when n is large enough, this probability value here can be well approximated by this Riemann integral. So when n is large enough, the probability value here can be approximated very nicely by this integral, by this Riemann integral, with this this function as the integrand. Well, the limit is true not only for an I, but also valid for more general choices of xi's. So as long as they are zero mean and unit variance random variables, surprisingly, we can always use this formula in color red, the second formula in color red, to approximate the distribution of such transformed random variables. So as long as xi's, suppose let's say IIDs with zero mean and unit variance, this one sometimes serve very nice approximation for the distribution of such monster. And the integrand inside here is the PDF function of the normal distributed random variable. So we say a continuous random variable z is said to have the standard normal distribution n, 0, 1. So this distribution is determined by two parameters. Here is the average. The second one is the variance. So mean 0 and variance equal to 1. If its PDF function is given by this function. Normally we use small fz to denote the PDF function. But this standard normal distribution is so important, they sometimes even get a specific letter to denote the density and its CDF, right? The small psi and the big psi, to denote the PDF of the standard normal distribution and the CDF of the standard normal distribution respectively. So if you have a distribution with PDF function like in this format, then it's a standard normal distribution. Well, if we consider this location transformation, location scale transformation, let's say x equal to mu plus sigma z, then the distribution of x is called the normal distribution with mean mu and variance sigma square. This is not very surprising. It's not a very surprising result because expectation of x is essentially expectation of mu plus sigma z, and the z has mean 0, so it's essentially equal to mu. What is the variance of x? Well, we don't care about we can shift by any constant, and the variance remains the same. Let's move the sigma square outside the bracket. That's sigma square times the variance of that, which is 1, so it's sigma square. Now the question is, what is the PDF function of x? You can pause the video at this moment and try to figure out yourself. Well, the PDF of x has this format, right? If you compare with the formula in color red, it's slightly different by including mu and sigma square here. How do we derive this? The derivation is also straightforward by first looking at the CDF. So the CDF function, cumulative distribution function of x, is the probability of mu plus sigma x smaller or equal to x. Then if we move mu to the other side and divide it by sigma on both sides, this is essentially, this is a mistake. It should be probability of mu plus sigma z, right? Smaller or equal to x, which then can be rewritten as if we move mu to the other side, which is essentially the probability of z smaller or equal to x minus mu, then divided by sigma on both sides. And this is the CDF function, right? It should be this number should be given by the CDF function of random variable z, right? So now we plug in the value here. And the fx is essentially the derivative of this CDF function. Given this CDF function is differentiable, conventionally choice will be the density should be the derivative. Now let's take a derivative with respect to this function. This is the result we have. So if we plug in x minus mu divided by sigma to this psi function and divided by sigma afterwards, you will have the PDF function of x. It looks very complicated, the psi function, right? But it is a proper PDF. So if we take a look at the function here, it's an exponential function. So it's always, well, non-negative, right? It's actually always positive for the whole real line. The next thing is to make sure this function is a proper PDF function, we also have to make sure this satisfies the second property, which is we need to make sure that the integration, if we integrate this phi z from negative infinity to positive infinity, we need to make sure it's equal to 1. And by a little bit tricky calculations, we can indeed to show that this is true, right? To show this one is equal to 1, let's show that it's, well, power 2 is equal to 1, right? This one to the power 2 is equal to, well, we know this integration is also equal to phi x dx, right? We just change the notations here. Then the integral value is exactly the same. So this value to the power 2 is equal to the product, if we integrate with respect to x, times this integral if we integrate with respect to y. Okay. Now we multiply them together. This step a little bit tricky. We're gonna work with the integration with substitution, and now switch the integration problem to a polar coordinates. From here, it's easy to say that indeed the integration value, the integral value is indeed equal to 1. So phi z is a proper PDF function. We're gonna make use of this property actually, the fact that this integration is equal to 1 in later discussions. It's very useful. This integration, this result is very useful to calculate certain integral values, as we're gonna show in later discussion of this video. So what does the CDF and PDF graph curves look like? Here I draw the CDF and PDF for the standard normal distribution with mean 0 and variance equal to 1. So indeed, right here, the middle area is indeed 0. The average of this distribution, well, the average of any random variable following the standard normal distribution is indeed has mean 0 here. Even by eyeball checking of this PDF curve, it seems to be the case. If you look closely with respect to these two curves, you can find this curve, well, for the PDF curve, it has a very nice bell shape, right, with the maximum value in the middle. And both graph, both the CDF graph and the PDF graph, they are quite symmetric. The CDF graph is a increasing function from 0 to 1 and very smooth. If you look closely, this is even a symmetric curve, well, central symmetry around this very point, 0, half. As for the PDF function, it's also symmetry around this middle area, right? So indeed, for this, we can observe some symmetry of the PDF function. It's a if it's a bell-shaped curve, and the value psi evaluated at z, for example here, is exactly equal to the value evaluated at minus z, right? For example, psi 1 is equal to psi minus 1. As for the CDF, it's centrally symmetric around this very point. So for the CDF function, big psi z is equal to 1 minus psi z. Therefore, what can you infer about the distribution of z and minus z? Apparently, they are not equal to each other, but their distributions are identical, right? If you look at the distribution here, what is the distribution of minus z smaller or equal to, for example, small z? That is essentially the probability of z larger or equal to small z. And we know for continuous random variable, if we if we add additional equality or drop the equality sign, the probability value remains exactly the same, because for a continuous random variable equal to a specific number is always of 0 probability. What is this function? It's the survival function of the z random variable, right? And based on this symmetry, this is exactly phi z. So the PDF function of negative z is exactly the same CDF function of z itself. Z minus z, they have the identical distribution, right? They also have certain symmetry. Now let's take a look. If we change the mean from 0 to mu, sigma to arbitrary numbers, what changes do we have concerning the CDF and PDF graphs? First, let's keep the sigma equal to 1. Let's fix sigma square equal to 1, but shift the average from 0 to 1. Well, we can see that indeed those curves shift from 0, right? The center shift from 0 to 1. Okay, so the average changes. And what happens if we fix mu to 0 but choose different values for the sigma for the variance? What changes can we observe from the graph? You can pause the video at this moment and try to figure out yourself. Well, the differences are quite interesting. Right here, we fix mu to be equal to 0, and sigma, the red curve is the sigma equal to 2. The black curve is, well, the black curve is the standard normal distribution CDF and PDF. And the blue curve is with a smaller value of the sigma. We can see that as this sigma square, as this sigma, right, reducing from 2 to half, the CDF function is getting sharper around the mean area, right? Around 0 is getting sharper. So more probabilities are assigned to area closer to the average, which is also reflected by the PDF curve as, right, from the red to black to blue, we can see the peak is getting higher and higher, and more probability densities are getting closer to the average value. This is not very surprising given the sigma here, right? Sigma square here is, well, describing the variance of this normal distribution. And the variance is the spread, or describe the distance, how far they could be from the average. And with a smaller variance here, they will be getting closer to the expected value, to the average value. So more probabilities, they are more likely, they will be more likely to be drawn from area closer to the average value. Okay. So for this normal distribution, you can see the shape is driven by these two parameters. As long as you fix those two parameters, you fix the CDF and the PDF for normal distribution. So if we recall our discussion about Z and minus Z, we say they have identical distributions, and here we have a second argument about that. What is the mean of minus Z? If Z follows the standard normal distribution with mean 0 and variance 1, what is the mean of the minus Z? We know it's again normal distribution, right? And the mean will be 0 as well if we make use of the linearity of the expectation. As for the variance, what is the variance of minus Z? This is minus 1 times Z. If we move the minus 1 outside the variance, it has to be to the power 2, which will be 1 times the variance of Z. So it's also normal distribution with 0 mean and variance 1. Therefore, by compare these two parameter values, we can also see that Z and minus Z, they have identical distributions, right? So this normal distribution is very, very special. Next thing, let's consider the expectation and variance. Well, in the formal definition, we already mentioned that for Z is 0 mean and variance 1, but let's verify that such density function indeed produce 0 mean and variance 1. So what is the expectation of Z by definition? Is this Riemann integral of x multiplied by the density function. If we take a close look of this density, it's a odd function, right? This is odd function. And the value from infinity to 0 cancels exactly the value from 0 to positive infinite. So altogether, they deliver 0. The expectation is quite clear. How about the variance? Right, we have already calculated the expectation of Z. We know the variance of Z is equal to the expectation of Z to the power 2 minus the average to the power 2, right? Here is already 0. Now we only need to calculate the expectation of Z to the power 2. Then again, by the definition of expectation and making use of the lattice, the law of the unconscious statistician, we know the expectation of Z to the power 2 is the Riemann integral of x to the power 2, small x to the power 2, multiplied by the density function here, right, from negative infinity to positive infinity. If we look at this function is an odd function. But this function is an even function. So the value of this integral is essentially 2 times if we only integrate from 0 to positive infinite. Right? This is an even function. So the integral value from negative infinite to 0 is exactly equal to the integral value from 0 to positive infinite. So it's 2 times this integral. To calculate this one, first we will make use of the integration by part. This is the result we have. And if you plug in 0 here, and it's basically 0. If you plug in infinite value here, then the exponential to negative infinite is essentially equal to 0, right? So the first part is gone. The question is, what is the value of this integral? Right? What is the value of this integral in the red box I just marked? If we look closely, this function, it looks like the density function, right? If we rescale by 1 over square root 2 times pi. And what is this integral value? This is essentially b the z larger or equal to 0, or it's also equal to the probability z is larger to 0. Recall that we have a very symmetric bell-shaped density, right? So the area from 0 to infinite is exactly equal to the size of the area from negative infinite to 0. And we know the total size under the PDF function is equal to 1. So this integral here is half of the 1, which is half. Therefore, we make use of the fact that the density will be integrated up to 1, and the symmetric of this density, so this is the half of 1. We can make use of the probability density function to help us to calculate integral values. Okay? And altogether, the expectation of that to the power 2 is equal to 1. Then what is the expectation of x? We know x has exactly the same distribution as mu plus sigma times z. We have already showed that expectation of such one is equal to mu, and the variance of x is equal to the variance of mu plus sigma times z, because mu plus sigma times z has exactly the identical distribution as the distribution of x. And what is the variance of this random variable? We know we can shift constant. The variance remains the same. The variance of a constant times z, if we move the constant side outside, don't forget the power 2, sigma to the power 2 times the variance of z. Variance of z here is equal to 1. So it's indeed equal to sigma squared. And we indeed verify that with the given PDF function, the z, the standard normal distribution, indeed have 0 as mean and 1 as variance. As for the x, it also has mean mean mu, and sigma squared as the variance. This is the initial introduction of this normal distribution. Thank you for watching this video.